My guest today is Ned Nikolov.
I would like to speak today and talk about a new climate paradigm, a theoretical paradigm in climate science, something that is based on NASA planetary data. And what we have discovered, this is a work that has been going on since 2012 so like 12 years. And what we have discovered and what we came up with as a concept, which is rooted in observations, not just a theory that you come up with, by conjecture or by thinking about it. It's very, very different from what people normally know about climate, what they hear from both sides, the mainstream and the skeptics. So if you have a problem understanding something, I encourage you to go back, listen again, because the whole thing is quite different. The whole paradigm is very different. So it is well known that the climate models are not successful in reproducing reality. And this is just an example, recent example of article published by Gavin Schmidt in Nature. This was an opinion article, but he pointed out that the climate models could not explain the 2023 heat anomaly. In 2023, we had a unusual warming that actually surpassed all the other warmings we have, at least since the satellite era began, which was in 1979. And Gavin Schmidt here says, all the theoretical drivers of climate, including greenhouse gases, aerosols, volcanic eruptions, and all that, could not explain the observed change in temperature, the observed warming in 2023. And he said, we are entering uncharted territory. Well, as we will see in this presentation, actually the direct explanation for this warming is very clear, and it's available from the satellite data, the very data that Gavin Schmidt actually cites and says that they've been very helpful to understand climate since the 1980s. And yet apparently he didn't look at the CIRRUS data, which is the most recent platform that measures radiative fluxes on the top of the atmosphere. And from those data, it's clear, and we will show this, I'll discuss about this in the presentation later on, that it was the albedo, the change in albedo, decrease in albedo that fully explains the warming that we have observed in 2023. Not only that, but the warming since 2000. So this is an example that, the current theory basically is failing. Is the model, if the climate models are unable to explain what is observed, that means there is something wrong with the models, which means there is something wrong with the theory. And indeed, there is a lot of stuff wrong with the climate theory. So I will start in an unusual way here. I will start with the conclusions or the findings, general findings that we have obtained in our research over the last 12 years. So first, I will talk about, the main premises of the new paradigm that we have discovered, and then I'll go into details and explaining more what it means and how we got to there. So the first thing is that the atmospheric thermal effect of the atmosphere is not 18 or 33 degrees, as you may have heard, and actually it's everywhere. You go on a NASA website, you look at in the literature, those are the numbers that are being used. And the reason why the range is 18 to 33 degrees is depending what kind of albedo they use in the Stefan Boltzmann equation to calculate the reference temperature, which means the temperature of the Earth without atmosphere or without any greenhouse gases. So the reality is that the thermal effect of the atmosphere is close to 90 degrees on Earth. The thermal effect of the Earth's atmosphere we're talking about, and which is about 2.7 times higher than actually has been assumed and calculated for the last 50, 60 years. The second fundamental premise that we have discovered is that the radiative greenhouse effect does not exist. This doesn't mean that the atmosphere doesn't create a thermal effect. We call this atmospheric thermal effect or enhancement, or ATE. But the ATE is a form of adiabatic heating caused by total air pressure that is independent of atmospheric composition. So pressure enhances the energy that we receive from the sun through force, because pressure is a force per unit area. And from the gas law, just to remind the audience, P times V, pressure times volume, actually equals joules, which is the thermal kinetic energy of the gas or of the atmosphere. Third, the baseline global surface temperature of rocky planets and moons is determined by the mean total solar irradiance and total surface atmospheric pressure. Those two variables, the solar constant, which is also known as total solar irradiance or TSI, and the total surface pressure determines actually the completely and accurately the global mean temperature, not only on Earth, but on a range of planets and moons across our solar system, and the relationship is extremely accurate. The atmospheric long-wave radiation is a byproduct of atmospheric and surface temperatures, and it is not a driver of climate. So it's like an effect of the atmospheric thermal effect. It's a byproduct of the atmospheric thermal effect. This is something that you'll never hear anywhere. We discovered this, and the first time we realized that, it was really a shocker to us, but I'll discuss this in more details later in the presentation. So what drives the climate? Well, on timescales of thousands to millions of years, the climate is driven by changes in total atmospheric mass and surface pressure. This was our finding, and I'll go into more details about this later. On timescales of decade to centuries, which is the human timescale of perception, the climate is basically driven or modulated by changes in cloud albedo, which apparently are driven by cosmic forces. That means the solar activity, magnetic activity, solar wind, probably indirectly the solar magnetic activity impacts the cosmic rays, which are responsible for creating the condensation nuclei for the clouds. But the mechanisms about the cosmic forcing of the cloud cover changes are not well known. However, there is absolutely no question from satellite data, as we will see later, that the changes in the cloud cover and the cloud albedo are basically the primary driver of global temperature on timescales of decade and probably to centuries. So this is the human timescale, the one that we can perceive. Okay, so what determines the magnitude of how much is the magnitude of the atmospheric thermal effect, or the so-called greenhouse effect on Earth? So there are two measures of the greenhouse effect. One is to the temperature, and the other one is to radiation. So first of all, the first thing we'll discuss is how the greenhouse effect is determined with respect to temperature. Well, the concept is very simple. One takes the observed global surface temperature on Earth at the present, which is about 288 degrees. The actual number is 287.6 Kelvin, but it's close to 288 degrees. That's what a lot of people use in their publications, in their discussions. And then from that, you subtract the temperature that's supposed to represent the global temperature of the Earth without atmosphere or without greenhouse gases. Now, in the climate theory, atmosphere that has no greenhouse gases is the same as lack of atmosphere in terms of global temperature. This is not true actually physically, but that's what the greenhouse theory asserts or assumes. So how they calculate the global temperature of the Earth without atmosphere, without greenhouse gases? Well, there is a thing called the Stefan Boltzmann law that relates absorbed radiation to temperature. And here you see the equations on the upper left side, where basically S is the total solar radiance or radiation above the atmosphere. Alpha sub P is the planetary albedo, and then you have the Stefan Boltzmann constant sigma on the bottom, and the emissivity of the Earth. So applying this equation in that form, using the actual observed albedo of the Earth, which is about 29% at the moment. People have used in the past 30%, but really the satellite data suggests that right now it's about 29%. We get a temperature that is close to minus 18 degrees Celsius. So when you do the difference between the observed surface temperature on Earth and that reference temperature, we get about a 32 degree 32 degree Kelvin. Now, the one thing that is very interesting here is that this reference temperature, T sub E, is supposed to represent the global temperature in the absence of greenhouse gases. Yet in most publications on that subject that you see, papers, textbooks, and so forth, you will notice that the albedo that they use in this formula is actually not the surface albedo of the Earth, which is around 13%, but actually they use the current present albedo of the Earth, which is affected by clouds. Now, clouds are composed of water vapor, and water vapor is the strongest greenhouse gas. So they say it's supposed to be the temperature without greenhouse gases, but then they're using the albedo of the clouds included in that formula, which it kind of doesn't make any logical sense. But that's besides the point. So if you use a 13% albedo, just the albedo of the Earth, you get even higher temperature than the minus 18 degrees. So then the overall greenhouse effect becomes even smaller. So it's around maybe 18 degrees or so. So in reality, what you have to compare here is actually a demonstration why this reference temperature derived from the Stefan Boltzmann equation is actually incorrect with respect to spherical objects. Because the Stefan Boltzmann law is a perfect physical law and it's well documented. However, it applies to isothermal surfaces. It doesn't apply to sphere that is heterothermal, meaning that radiation is being absorbed at different rates at different latitudes because the absorption is a function of the cosine of the incident rays. And basically you have a large variations of temperature over a sphere that has no atmosphere or airless body. And because of the nonlinearities involved in the Stefan Boltzmann relationship between radiation and temperature, you can see here to the power of 1/4, condition arises where when you apply this formula to, say, for example, the temperature of the moon, you get very different result from the one that's actually measured by NASA. And on the right-hand side here, this is actually temperature readings from the Diviner project. It was a project that went on for several years, and they mapped the temperature of the moon using infrared remote sensing with high accuracy and high resolution, like 1/2 degree throughout the entire moon. So this curve here represents the variations of the moon temperature as a function of latitude, and as a result of I processed this data. I actually received the data from the author of this paper. His name is Williams. In 2017, he published a paper about the moon temperature results from the Diviner data. So I obtained the data, and you're looking here, every single point here represents, a lot of readings. Basically, the whole curve is the result of over 22 million readings that were in the database. So here you see the raw calculations of the points in blue, and then the dark curve actually is the polynomial fit to those points, and the fit is pretty accurate. So this curve could be used to calculate really accurately the global surface temperature of the moon, and the value that it produces is about 199 Kelvin. Now, if you compare this to the calculation that would come from the Stefan Boltzmann equation using the appropriate albedo of the moon, which is 13%, and the solar constant or TSI S is actually the same value as for Earth, because Earth and Moon has the same distance. So you get a value of about 270.2 Kelvin, and this value produced by the formula is about 71 degree Kelvin higher than actually the real global temperature of the moon. So that's a huge difference. Why is that? Why the Stefan Boltzmann equation cannot produce the correct temperature of the moon? Well, the reason is purely mathematical. And here on this slide, on the left, it shows a screenshot of a paper that we published back in 2014 that explains why the simple isothermal form of the Stefan-Boltzmann equation cannot calculate correctly the average global temperature of airless bodies. Those are bodies, planetary bodies that have no atmosphere, like the moon. So on the upper, on the right-hand side, you can see the Stefan-Boltzmann equation, the effective emission temperature T sub E shown again, and then below you have the another formula which was derived in this paper 2014, where we have applied the Stefan-Boltzmann equation on every point on a sphere, and this is a result of a spherical integration of a Stefan-Boltzmann law that produces this formula. This formula actually reproduces correctly the observed temperature of the moon, right? Because it is spherical integration of the actual temperatures that are a result of the Stefan-Boltzmann law applied at individual points on the surface of the moon. So the net result is that for airless bodies, this is the main conclusion from this paper, for airless bodies, the T sub Na, which is the temperature of the body without atmosphere or no atmosphere temperature, is always much, much smaller than T sub E, which is the effective emission temperature. So in the paper, we discussed the mathematical reason for that, and it's called Hildreth's inequality between integrals. I will not go into details now, but I encourage the viewers to look up this paper. The actual link to the publication is shown under the screenshot of the abstract of the paper. Now, you may notice that the paper is the authors of the paper, Dan Volokhin and Lark Rilez. This was our first attempt to publish something that is non-conventional, and we had a great deal of resistance from reviewers and journal editors. So we tried a number of journals. It was rejected for reasons that have nothing to do really with the content of the paper. The critiques were really very funny. So we realized that at that time we were known already that we're kind of skeptics in the climate arena. So we decided to change our names and use the pseudonyms. And the pseudonyms that we use basically are our names spelled backwards. And that thing was, this happened in 2014. So then there was another paper we tried to publish by the same way in 2016 that made, waves, and it was discussed online. And you can find, if you just Google Volokhin and Rilez, and you can find the whole story. But we did that in an effort to force the reviewers to focus on the content of the paper and not be distracted by who the authors are. And it turns out that in science, using pseudonyms is not an unusual thing. In fact, there was a paper published in 2013 where the title was Anonymity in Science, and the author actually used a pseudonym to show his name. It was not his real name. And he talks about how in science, for different reasons, this trick has been used, including some famous examples. It doesn't come to mind now, but there was a guy in statistics who used, I think, the t-test or something. The author, when they first published, he used a fake name, and the reason was that because he was famous at that time, he wanted to see if this is published by someone that people don't recognize, what will be the actual response and what will be the critique, because otherwise he thought that, he published under his name, people will not dare to critique him, right? So anyways, we had a different reason. Our reason was that we could not get a fair assessment, fair review, and we had to hide our identity. And the way we hid our identity, didn't come up with something totally different name, is just our name spelled actually backwards. So Dan Volokhin is Ned Nikolov if you read it backwards. So anyways, that's an interesting detour. So the other definition of okay, before I go to that, I want to point out here that based on this analysis in this paper, we have discovered that the thermal effect of the atmosphere on Earth is around 90 degrees, and it's not 18 or 30 degrees, so much, much higher than actually assumed in the climate literature. The other definition of the greenhouse effect is the so-called radiative definition, And in fact, in climatology, in official climate science, this is considered more important and more relevant to defining the greenhouse effect than the one through temperature. So this is a energy balance diagram from 2013 IPCC Assessment Report 5. I'll show that another diagram later on with the current assessment report, which is 6 from 2021. They're basically identical. There is no difference, maybe just the last digit in some of the fluxes, but for all practical purposes, they're identical. So basically, the way the greenhouse effect is defined in the literature through radiation is through this difference in the flux in the outgoing long wave flux from the surface, and the differences between the surface flux and the one measured at the top of the atmosphere. And in this case, the orange arrows show the long wave radiation. So if you look at the orange arrow that is pointing upwards, you can see that the flux of the surface is about 398 watts per square meter. And on the top of the atmosphere, what is measured is about 239, 240, watts per square meter. So this difference of 159 watts per square meter is considered the greenhouse effect. And the interpretation is that this is caused by greenhouse gases. The long wave radiation is being absorbed by greenhouse gases. And this absorption causes actually the thermal effect of the atmosphere. Now, this definition was proposed, to my knowledge, for the first time in 1989 by Raval and Ramanathan. I think Ramanathan is still alive. He's in California. Ramanathan is the one who designed this ERB experiment, Earth Radiation Budget Experiment, which was the first attempt to measure radiative fluxes on a global scale through satellites. And in one of his articles, actually, in one of his papers, he actually points out that the reason for this experiment that he pushed NASA to launch was exactly the main reason. It was other reasons, but the main reason was actually to measure the greenhouse effect, because this is how he portrayed. If you have a flux from the surface and you have something measured on the top of the atmosphere, the difference should reflect the absorption of the radiant heat by greenhouse gases. And if you look at that on the surface, oh yeah, it makes sense, right? People say, yeah, sure, it makes sense. Well, so in more recent times, here are two papers by Van Garden and Happer, one published in 2019, the other one published in 2023. Now, both of those papers are kind of manuscripts that, they've been shared around and discussed a lot, but they're not officially published in terms of, they're not peer-reviewed publications. I don't know why they didn't try. Maybe they had resistance, from, the mainstream, but, regardless, you should find a way to publish those instead of having them like a manuscript and using, especially when they're used in discussions. So the first paper, 2019, if you noticed, it's called Infrared Forcing by Greenhouse Gases. So those papers basically present the mathematical apparatus and claim to explain how the greenhouse gas radiative forcing works. Now, the thing to point out here is that both those authors are climate skeptics. However, they do fully support the idea that the greenhouse effect is a radiative phenomenon, and it's caused by the long wave radiation that is emitted from the Earth and being absorbed by the greenhouse gases and then re-emitted and so forth. So this is a standard thing that they do not dispute. The only thing that they dispute is that the effect of increasing CO2 in terms of creating radiative forcing and global temperature change is much smaller than the climate models predict. So that is their main argument, basically. So they're arguing about the magnitude of the CO2 effect. They're not arguing about the principle, and they do not refute, they do not deny that increase in CO2 would cause a temperature change. Okay. So here is the 2019 paper. In the very introduction, there is a definition how they define the radiative forcing, and the sentence reads: greenhouse warming of Earth's surface and lower atmosphere is driven by radiative forcing, F, which is the difference between the flux of thermal radiant energy from a black surface through a hypothetical transparent atmosphere, and the flux through an atmosphere with greenhouse gases, particulates, and clouds, but with the same surface temperature. Now, this sentence is basically the same definition of the same thing that Ramanathan used to define the greenhouse effect, but they, instead of greenhouse effect, they call it radiative forcing. If you read the sentence, it becomes clear. The thing you have to realize is that, and they discuss this in those papers, especially in the 2023 paper, they state explicitly that if there were no greenhouse gases in the Earth's atmosphere, the troposphere will be isothermal. That means there will be no temperature change from the surface to the top of the troposphere. And as a result of that, the long wave flux that comes from the surface will be unabsorbed, unimpeded, unattenuated, and the same flux that is on the surface, you will see it on the top of the atmosphere. So their presumption is that it is the greenhouse gases that actually create the lapse rate, and it's the greenhouse gases that actually cause the attenuation of the long wave flux going up to the top of the atmosphere. Now, this is a pure assumption that they stated in the papers, and there is absolutely no empirical evidence or observations that they show. In fact, the standard atmospheric physics refutes that, and it's it's the core of the confusion in the greenhouse theory. And I'll show this in a minute. So going back to the radiative definition of the greenhouse effect, this slide actually demonstrates how illogical this is. So the lower graph that's shown here as figure 1, the figure on the lower right corner is actually from a paper by Sun et al., I think 2016. And this is based on satellites. So they calculated the greenhouse effect based on the standard definition, which is the difference of long wave flux from the surface to the top of the atmosphere. And this is a map, global map of those calculations, right? So as you can see, the highest number of this index is actually in the tropics, and the lowest number, which is close to 0, is actually at the poles. So according to this definition, the greenhouse effect should be strongest at the equator and weakest to the poles. Well, if you compare the actual thermal effect of the atmosphere, which is assessed against the temperature profile of the moon, because moon, in our 2014 paper, we have a whole section that discusses why the moon is the perfect airless equivalent of Earth. It is at the same distance from the sun. The surface albedo of the moon actually is very, very close. Surface albedo of the moon is about 13.8%, depending on the estimates. Some actually use 13%. The surface albedo of the Earth, without clouds and everything else, is also 13%. So we have a great deal of similarity. Even we have oceans that are very dark, but then we have continents and deserts that are very light. So on the average, the albedo of the surface of the Earth, excuse me, is about 13%. So in order to compare the thermal effect, to calculate the thermal effect of the atmosphere on Earth, we have to compare the temperature profile throughout the latitudes to the temperature profile of the moon. And the figure 2A on the top, on the upper right corner, actually shows those two profiles. So the blue area in the middle actually is the thermal effect of the atmosphere. The figure on the lower right, it shows the difference for every latitude between the Earth's average temperature and the moon's average temperature. And as you can see, this is basically the thermal effect of the atmosphere. As you can see, the thermal effect is the smallest, relatively speaking, at the equator and the largest at the poles. This is the exact opposite pattern of the pattern one obtains by using the standard definition of the radiative definition of the greenhouse effect. So something is here off. Something is off. So furthermore, there were two papers published, one in 2015 and one in 2018, that applied the standard definition of the greenhouse effect as a flux difference of long-wave radiation between surface and top of the atmosphere over Antarctica. And this is based on satellite observations. And both teams, the independent teams, they both report that according to this definition, the way it is calculated, the greenhouse effect, over Antarctica, that effect is 0 or negative. In other words, if there is no thermal effect of over Antarctica, you would expect that Antarctica, central part of Antarctica, would have the temperature of the center of the south pole of the moon. Well, that's not the case, because on the south pole of the moon, the temperature is about 90 degrees, right? So you have about 140-degree difference between the temperature above central Antarctica and the south pole of the moon. So this is an example that this radiative measure of the greenhouse effect as a flux difference makes no physical sense, because there are regions around the poles where this measure produces 0 or negative greenhouse effects. And you could not have that because we have atmosphere. It could not be 0, right? So another thing, this is something that everybody agrees in climate science, that the greenhouse gases somehow trap heat. So the trapping of heat is, they call it, different terms. Trapping of heat, impeding of the cooling, slowing down of the cooling, all those terminology. But they're essentially coming to, the bottom line is that the assumption is that the thermal effect of the atmosphere is caused by the greenhouse gases that absorb and retain heat, right, in the Earth's atmosphere. Now, this trapping of heat is actually refuted by the satellite data. This graph shows comparison of the surface temperature observations that come from, this is the average of 6 data sets, and it's described in one of our papers, the most recent one in 2024. And then we have the observations from CIRRUS, which are the best available observations right now of the outgoing long-wave radiation, outgoing long-wave radiation, OLR, on top of the atmosphere. And the thing to notice here is that the two curves, the outgoing radiation in blue and the surface temperature in red, they totally match in phase. They're both increasing. The warming causes the long-wave radiation going out to increase, but they are also in phase, which means that those two curves represent actually their 13-month running means. And so they are in phase, which means that there is no indication of any trapping. If there was trapping of heat, there should be some delay. The outgoing radiation should actually lag the temperature response, but it doesn't. So within a 1 year, because this is a 13-month moving average, basically annual data, within 1 year, in this time scale, they are perfectly aligned. So that's another indirect evidence that there is no trapping of heat going on in the atmosphere. Now, what is the problem? How we can explain actually what is the real physical explanation for this decrease of the surface flux as it goes through the troposphere and before it exits the atmosphere and goes to space? Why this flux goes from 398 watts per square meter and being reduced to 240 watts per square meter, right? In fact, the surface flux, if you look at the total surface energy flux, it's not 398, but actually it's 501, simply because we have sensible and latent heat fluxes, which are turbulent fluxes, which also occur on the surface. They're energy fluxes. They're not radiation, but they're part of the total energy flux. So when you add 398 plus 82 plus 21, you get a 501 watts per square meter on the surface. And on the top of the atmosphere, you only measure 239. Why is that? Well, standard atmospheric physics provide the answer. The reason is that the energy content of the atmosphere of the troposphere drops with elevation because the temperature, the pressure drops. So there is a pressure decrease with height, And the pressure decrease with height is such that in order to have a stable atmosphere, it comes from a condition called hydrostatic equilibrium, which means that at any level in the atmosphere, on average, the outward push of pressure has to be balanced by the inward pull of gravity. Without having this balance, the atmosphere would either collapse on the surface or get, dispersed in space. In order to have a stable atmosphere, you have to have this hydrostatic equilibrium. So now, as a result of this hydrostatic equilibrium, there is mathematical derivation. You can show that this is the reason why the pressure decreases with altitude. Now, in the troposphere, the thermodynamic process that is governing the function of the troposphere, it's called a polytropic process. The polytropic process is a wide range of processes. One of them that it includes is actually the adiabatic process. Adiabatic process is where you don't have input or loss of energy or loss of heat by a parcel of air, but the internal energy and temperature of the air changes when the parcel, for example, goes up. It expands, and this expansion does work. It pushes on the air around it, and as a result of this expansion, the energy content of the parcel drops and the temperature drops. So basically, the change of temperature from the surface to the top of the troposphere, the so-called lapse rate, is actually a result of the decrease of pressure with altitude. And the polytropic process, I have a few equations here that actually are just explained in more details in our latest paper from 2024, published in August. It basically says that the product of pressure times volume to the power of n, volume is to the power of n, is called the polytropic index. N is the polytropic index, is constant. The value of n, it can have a wide range of values, but in the atmosphere, it's typically between 1 and 1.4. There is a reason why it has those values in the atmosphere. So when the polytropic index would be 1, in theory, it doesn't happen in practice, but in theory, that means you have an isothermal atmosphere. If you have a 1.4, a polytropic index of 1.4, you have an adiabatic atmosphere. In our atmosphere, because of the presence of water vapor, which transports heat from the surface and releases in the higher altitudes when it condenses, the polytropic index actually, it's a little bit below, it's between 1 and 1.4, and the actual value is something like 1.23. So the process in the troposphere can be thermodynamic. It can be described as quasi-adiabatic. That means that majority of the decrease of temperature with altitude and dropping also the energy flux with altitude is because of the drop of pressure with altitude. But there is also loss of little bit of energy to radiation and other processes, but which is why we call it a quasi-adiabatic. It's not a fully adiabatic. Regardless, the point being is that in the troposphere, temperature is related to pressure. As pressure drops, so does the temperature, and the adiabatic lapse rate, which is actually the backbone of the lapse rate in the troposphere. Lapse rate refers to the decrease of temperature with altitude, or the change of temperature with altitude. In the troposphere, it is negative. That means for example, every kilometer or so, you have about 6.5 degree drop in temperature. Well, the adiabatic lapse rate, dry adiabatic lapse rate, is the backbone of the lapse rate because it defines the neutral stability conditions in the atmosphere. And when you look at the derivation, how you derive this formula for calculating the dry adiabatic lapse rate, it basically is the change of pressure of temperature with pressure times the change of pressure with altitude. And after you go through the math, the final formula is actually the pressure gets canceled. The final formula actually is dry adiabatic lapse rate equals gravity or gravitational acceleration divided by the specific heat of air, C sub P. Now, this formula produces for Earth about 9.8 Kelvin drop of temperature for every kilometer. The actual drop in temperature is about 6.5, and that's because, like I mentioned, the water vapor, which gets evaporated at the surface, it takes heat away from the surface, but then once it raises up, it goes into lower temperatures, it reaches a saturation point, and it condenses, and in the process of condensing the water vapor, it releases the heat that was absorbed in the surface. So releasing that heat of the higher altitude actually makes the lapse rate less than the dry adiabatic lapse rate, and it makes it to about 6.5. Now, the interesting thing about all this discussion is that, for example, Happer and Vargarden, they assume, and they specifically say that in their papers, that without the greenhouse gases, the troposphere will be isothermal. So there will be one temperature from the bottom to the top. Well, so the water vapor is the strongest greenhouse gas. And yet the physical reality is that adding water vapor to a dry atmosphere, it reduces the lapse rate, because the original lapse rate of the dry atmosphere is higher than adding the water vapor. So the water vapor kind of moves the lapse rate towards isothermal. It never reaches isothermal, but it moves it in that direction. So the actual physics of the atmosphere is the exact opposite of the assumption that eliminating the greenhouse gases will make the atmosphere isothermal, which is not true. What makes the atmosphere, what makes the lapse rate is actually the change of pressure with altitude and the dependence of temperature on pressure. And here I have the equations that, those are discussed in our paper. But so we have the reason why the surface flux gets attenuated, and the attenuation coefficient is like, the ratio of the surface flux of the infrared flux at the top of the atmosphere, 239, divided by the total flux of the surface, 501, it's about 0.48. In other words, close to 52% of the surface flux gets attenuated or adiabatically cooled. That means the energy in that flux is being dissipated. There is no energy. So measuring the greenhouse effect by this in this way, by taking the difference of the surface long-wave radiation minus the top of the atmosphere long-wave radiation, makes no physical sense once you understand what is causing this attenuation of the flux. Because that attenuation represents the loss of energy, adiabatic loss of energy in the atmosphere. It does not represent absorption of heat by the greenhouse gases. So in other words, the greenhouse effect, and also what Happer calls it radiative forcing, is ill-defined because they're calculating energy, they're using energy that doesn't exist. It's not, again, it's not an absorption of the long wave or total flux by the greenhouse gases. Is actually dissipation of the energy that's coming from the surface by through a mechanism, adiabatic cooling mechanism, which means the flux is going through progressively lower pressures as it moves up in the atmosphere, and that causes the cooling. So the energy is gone. There is no accumulation of energy. There is no trapping of heat. Was this understandable to you?
I definitely need to think about it some more, but yeah, it's a good explanation.
So the confusion has been that this polytropic thermodynamic process that governs in reality that the dynamics of the troposphere has been misunderstood, forgotten, and ignored by the people that focus on the radiative transfer only. That's the point. And
can I ask you, maybe at this point, you had on a previous slide, you had that T sub NA for no atmosphere.
Yeah.
I just wanted to check to see, can we do that computation on other bodies other than just Earth's moon? Can we use it on other moons and any other planets that are rocky with no atmosphere to make sure that works?
Yes. So T sub, you're talking about the temperature without no atmosphere, the big expression here. Is that what you're talking about?
Yes. Yep.
Yes, of course. And we have used that in our discovery when we discovered what is the thermal effect of the atmosphere, which I'll go in a minute about. This is the equation that we use as a reference to calculate the no atmosphere temperature of any planetary body and then compare it to the actual temperature under the atmosphere that the body has. So we're using that.
All right. But this one point is one major departure between conventional climate science and you,
Yes.
right? This one point. Yeah.
Right. This is very important because, again, the standard Stefan Boltzmann law shown here on the top, it always overestimates the actual no atmosphere temperature of a planet. Always. The actual magnitude of the overestimation is larger when you get closer to the sun, and it becomes smaller when you go away. But in terms of relative, it's always in error. So
okay, thanks.
Okay, let's go. Okay, we saw this. Okay, so so after we realized that, we decided to actually take a whole different look at what is the nature of the atmospheric thermal effect. And the way we approach this is we said, okay, there should be universal mechanism that explains the atmospheric thermal effect on all planetary bodies in the solar system that have rocky surfaces. This is very important. We're not dealing with planet giants, gas giants that don't have surface. So if they have a surface, we don't know where it is, right? We're dealing with bodies where measurements have been done on the surface with sufficient accuracy so we can use them. And what we found is that those 6 planetary bodies that you see here on the left are the ones that have good measurements and over the last 40 years. And some of them have direct measurements because there have been probes that have landed on the planet. Others have remote assessments, remote measurements. But basically, it's Venus, Earth, of course, Moon, Mars, Titan, which is a moon of Saturn, and Triton, which is a moon of Neptune. If you look at this 6 planetary bodies, you'll see they span pretty much the whole breadth of the solar system. I mean, we're talking about in terms of astronomical units or distance from the sun, from a 0.7 astronomical units for Venus to 30.07 astronomical units for Triton. So it's a huge range, which includes a huge range of thermal regimes, temperatures, atmospheric compositions. Venus has the thickest atmosphere that we know of of the rocky planets on the solar system. And then, down to the moon where there is no atmosphere and everything in between. And Titan, for example, has about 50% higher atmospheric pressure than Earth. So, it's a smaller body, but it has a lot bigger atmosphere than Earth, right? So in terms of composition, you have Venus is mostly carbon dioxide. Earth is mostly nitrogen and oxygen. Moon is argon and some other little gases, but basically the atmosphere is 0. Mars is mostly also carbon dioxide. Titan is mostly nitrogen and methane, and Triton is mostly nitrogen. So really a huge diversity of atmospheric compositions, radiative regimes. So if we can derive a relationship that explains accurately the surface temperature of all these planets and moons, that should give us an insight about what is the thermal effect, the nature of the thermal effect of atmospheres anywhere in the solar system, right? So that was our thinking. So we applied a technique called dimensional analysis. It's explained in our 2017 paper, which I'll show here in a minute. But basically, the result of this dimensional analysis was that the relative atmospheric thermal effect, which is defined as a ratio of the temperature of average global temperature of a particular body to the temperature of that body without atmosphere, or the temperature the body would have with no atmosphere. This defines the atmospheric thermal effect. We call it relative because it's not, it's a dimensionless number. It's just like a percent, like a 1.5, 1.3, something like that. So this relative atmospheric thermal effect had a very strong and accurate relationship with total pressure. Now, the relationship is highly nonlinear. The red curve here is derived through regression analysis. And the bodies that participate in this regression analysis were all the planets except Titan. Titan was used as a kind of independent point. Now, some people say, well, you only have like, 5 points here, right? Well, this is what we have in the solar system, but the thing is that those 5 planetary bodies span an enormous range of conditions. I mean, the range is much, much bigger than anything you can encounter on Earth. And for all practical purposes, I have to point out that the greenhouse theory emerged on Earth. It was kind of tailored to the Earth. And yes, they applied to the other planets, but the funny thing is that if you take a climate model, standard climate model, which they're very sophisticated pieces of software, like 500,000 lines to 1 million lines of code, you take a model that has been run on Earth and does a relatively good job, say for the last 40 years or something like that, and you try to run it on Venus without any adjustments of the parameters, just using you're using the conditions on Venus, the models crash. They numerically become unstable and crash. So that tells you that there is something that is not right. If the models actually represent the true physics, they should not be crashing like that. So anyways, this curve actually gave us an idea what the thermal effect, what the nature of the thermal effect of the atmosphere is, not only on Earth, but on all those bodies that span the conditions of the solar system. And that is that the atmospheric thermal effect is a form of a pressure heating. In other words, it has nothing to do with radiative properties of gases, because it's a form of adiabatic or compression heating, which is independent of atmospheric composition. Now, this is very, very important. Like I pointed out, the atmospheric composition along those 6 bodies varies widely, yet the equation that produces this accurate results and accurately describes the variations of global temperatures across all these planetary bodies, it only uses global total surface pressure. And the composition is not present there. The other thing which is not present there is actually accounting for differences in albedo. And that's a very interesting thing. When we saw this relationship, we were really puzzled. How come you can have this accurate regression line by not accounting for differences in albedo? And if you look here on the left, the table with the planets, albedo is marked with A. So Venus has 90% albedo. Earth is about 29%. Moon is 13.6. Mars is 25%. Titan is 26.5%. Triton is 65%. So the variations of albedo, the range is pretty wide, from 13.6 to 90%. That's a huge range. And yet the equations does not use that, and the regression analysis, the dimensional analysis that we applied did not produce this as an important value. In fact, it's not even a variable. So how can we explain this? Well, the physical explanation is that this curve actually represents the baseline temperature, and it is the baseline temperature that is related or explained or determined specifically by pressure and total solar irradiance on top of the atmosphere. But this baseline temperature, it actually gives rise to a baseline albedo. So the bulk of the albedo, or the absolute value of the albedo, is actually a byproduct of the climate system itself. That is the conclusion from this curve. It's not a driver of climate. I mean, I'm talking about the absolute total value of the albedo, like 25% or 90%. It's not the driver. It's actually a byproduct of the operating of the climate system on that body. This is a whole different concept that is not present anywhere, and we concluded that just by doing our analysis. We didn't come up with this as a preconceived notion. It was an attempt to explain why you can have this accurate curve in red describing the temperatures of all these planets and moons without accounting for actual changes in albedo, across the spectrum of planetary bodies. Now, this does not mean that if you have a variations of the albedo around the baseline, that it would not affect the global temperature. It would. And actually, we have a derivation other equation that I'll show here in a minute that show exactly that. This is an extension of our original model that shows that when you have a fluctuations of the either TSI or albedo around their baseline values, you do have an impact on the global temperature, and we have equations to quantify that, okay? So on this slide here, just to point out, this is the actual expression, the equation that's on the bottom. It's like I said, it's a highly nonlinear, it's a double exponential equation, and it was derived from using regression analysis, right? This is not a theoretical equation derived from. Now, the interesting thing is that notice how this curve, the shape of this curve. Here, on the very left, you see the same curve, but then on the middle and on the right, you see curves that are also relating temperature ratios to pressure ratios, but then different systems. So the one in the middle is actually the so-called Poisson formula, or the compression heating of dry gas. And it's a formula that's derived from the gas law and the first law of thermodynamics. It's a well-known formula. And if you look, it also has a ratio of temperatures related to the ratio of pressures. But the interesting thing is that it has similar shape. Numerically, it's very different from the planetary curve, very different. But qualitatively, in terms of shape, it's very similar. The other curve on the very right actually is a form of the Stefan Boltzmann radiation law. And this is something that a lot of people don't realize, is that radiation flux, which is measured in watts per square meter, when you decompose them in terms of physical units, watts per square meter equals pressure times the speed of the moving particles. Pressure times speed equals watts per square meter. That's a result from the dimensional analysis. I can go through the derivation, but we don't have the time to do that. So that allows the Stefan Boltzmann law, which relates radiation to temperature, to actually express it in terms of a temperature ratio related to a pressure ratio. This is the pressure of photons. So it is true, and also a lot of people don't realize that radiation has pressure. So much so that Japanese use that physical fact to design a space, a probe, a space probe that they sent in direction of the sun, and they're using the radiation from the sun to propel the probe, because radiation, it has pressure. So basically, you have a pressure of photons times the speed of light. So the speed of light is very huge, like 300,000, close to 300,000 kilometers per second. So the pressure is very small, but if you have a lot of radiation, it does create and if you have a frictionless environment like in space, it does create enough pressure that you can propel actually the satellites. And I think that radiation pressure in some cases have interfered with the orbits of our satellites, and they have to be corrected because it changes the orbit. So the lesson here is that pressure is present in every system that has energy and temperature. You cannot have energy and temperature in a system without some form of pressure. Why? Because pressure is force per unit area, and the product with respect to gases, the product of, for example, the product of pressure times volume equals joule. This is something that even some scientists don't understand, don't actually, well, they may know it, but it doesn't come straight to their mind when they're looking at a physical system. And I had a response from one of the reviewers of our papers. He says, well, because I mentioned the gas law and so forth, he says, well, the gas law is just a relationship with between some variables. It doesn't mean much. And I pointed out to him, I said, pressure times volume is a definition of joule. He says, no, that's not true. I said, well, here, look at this Wikipedia article, One definition is Newton times distance, basically force times distance. But when you take into account that pressure is force time by unit area, and pressure times volume becomes basically a force times the distance, and you have energy. Okay. So the point being here is that the energy of any system requires pressure of some kind. And by changing the pressure of the system, you can change the energy content, and you can change the temperature. So the relationship that we have derived across the planet is not just a correlation, a coincidence that some people say, oh, just you can fit any curve here. Actually, no. If you try to fit say a fifth order polynomial to those points, yes, it will go to the points, but in the middle, it'll have this wiggling like this, and it makes no physical sense. There is only one equation, double exponential equation, that can fit accurately those points. And now this equation is not directly derivable from the gas law, because you're talking here a climate, planetary climates, as opposed to the other curve that we see in the middle and on the right that are actually very simple systems, right? So, but in terms of quality similarity, in terms of qualitative similarity, you can see that they are very similar with each other in terms of overall shape. Okay, so here's the equation that actually, it's a universal equation for computing the long-term baseline global temperature of any rocky planet and moon in the solar system and probably beyond. I mean, we don't have verification for other planets because we don't have, measurements of planets outside the solar system. But the equation should hold because it's based on fundamental laws, and it's based on statistical regression analysis that covers a huge range of atmospheric conditions and regimes in the solar system. So this equation, it gives you the baseline temperature of any planetary body, a rocky planetary body. It consists of two parts. The first part, and it's pointed here with arrows, is the global airless temperature of that body, the temperature the body would have if there is no atmosphere. The second term is the pressure enhancement term. This is the pressure-induced thermal enhancement, which is dimensionless quantity. So you basically you increase the temperature due to the presence of atmosphere and pressure by a certain percent. And you can say that this double exponential equation quantifies that relative increase of the temperature due to pressure. This is our paper that we published in 2017 that describes dimensional analysis and our analysis of all the planets. And I recommend to anyone who wants to actually learn about our climate concepts to really read this paper, because it's the cornerstone of our discovery of our new concept. The nature of the atmospheric thermal effect has nothing to do with the radiative properties of gases, and everything to do with the total pressure, because it's a adiabatic form of heating. So it's a thermodynamic phenomenon, not a radiative phenomenon. Now, we have extended, since our publication 2017, we have extended our baseline temperature model to include calculation and prediction equations that predict the temperatures of other latitudes, not just the global average temperature on a planetary body. And the way we did that, we applied dimensional analysis also to a few planetary bodies, Moon, Mars, Earth, and Titan, for which we have good data that define the variations of temperature, surface temperature with latitude. And in this case, we averaged the northern and southern hemispheres of every body, each one of the planetary bodies, and we came up with a single profile that gives the temperature change on the surface as a function of absolute latitude. Okay, so then we conducted a dimensional analysis, and we found that the relative thermal gradients. Our idea was to tie the temperatures of individual latitudes to the global value through the temperature gradients. In other words, the difference between the global temperature and a temperature on a particular latitude, what is controlling that difference, this temperature gradient, okay? So in this case, here is just the temperature gradient between the equator and the poles on every planet. And the dimensional analysis produced a curve, and after you take the anti-log, you actually get the physical curve, a very nonlinear relationship between that relative thermal gradient and molar density of the average molar density at the surface of the planetary body, okay? The atmospheric molar density, it makes sense to be predictor of the temperature gradient, latitudinal temperature gradient, because the more atmosphere you have, the higher the density in terms of particles per unit volume, the higher the ability to transfer heat across latitudes. If you don't have the reason why our poles are so much warmer than the poles of the moon, because we have atmospheric pressure, which is sizable, about 1 bar on average, and there is ability of the heat to be transported through the atmospheric currents, and there are all kinds of mechanisms, but to transfer heat from the equator to the poles, right? And this transfer of heat requires particles that do that, and it makes sense. And this is what the relationship shows, that it is actually the molar density, which is just the number of particles per. Doesn't matter what molecule it is, doesn't matter what kind of gas it is. It's just the number of particles per unit volume. Now, the other interesting thing is that the audience probably have heard the Avogadro's constant, which defines the number of particles in any mole of any substance. It is the same value, about, what was it, this 10 to, I forgot the value, 2.6 times 10 to the power of 23, a large number, very large number. But the point is that Avogadro's constant, it defines the number of particles of any molecule in any 1 mole quantity of any substance, okay? So here, because the molar density is the one that predicts actually the thermal gradients, it means that the composition, again, of the gas is irrelevant. It doesn't matter what the atmosphere consists of, right? So on the right-hand side here, you see the equation actually that describes that. And because the molar density, average molar density near the surface is a function from the gas law, is a function of pressure and surface temperature, you can describe this equation and cast it in forms of pressure, temperature, and in the gas constant, right? This is the expression here on the bottom. This is just one example of an equation that gives you the latitudinal temperature gradient, relative latitudinal temperature gradient between the equator and the poles. And the thing to notice here is that as the density increases, the gradient decreases. And when you get to the point of Venus, we don't have here Venus because Venus is isothermal. This curve really predicts isothermal conditions, meaning that the temperature between the poles and the equator on Venus are the same. And that's actually a fact. There's no difference because of the huge pressure and the huge density, right? So this graph shows, those two graphs show 2 other examples of relative latitudinal temperature gradients. And the one on the left is actually the difference between equatorial temperature and the global surface temperature divided by the no atmosphere temperature. And this has a similar shape. In other words, with increasing molar density, this relative gradient shrinks to the point that it totally disappears when you have enough, you have a high enough density, right? On the right-hand side, we have the difference between the global temperature and 60-degree latitude, and that difference divided again to the or normalized by the no atmosphere temperature of the body. And in a similar fashion, we have a decrease of that gradient, relative gradient. It drops as the molar density increases, right? As the density of the atmosphere basically increases. So the other extension that we did to our model was to, like I mentioned before, was to calculate the effect of variations in albedo and total solar irradiance around the baseline values, the effect of those on the global temperature. In other words, how delta S, which is the variation in the solar constant, so-called solar constant, it's not a constant, but people use that term, and also the variation in the albedo delta alpha, how they impact the delta T, which is the the variations of the global temperature around the baseline. Now, the baseline again is set by the baseline values of the solar constant, TSI, and the total pressure. But then you have the variations and it's primarily in the albedo. The effect of the changes in solar constant on global temperature is very small, marginal. You can for all practical purposes, you can actually ignore it. But the main driver of the changes in global temperature around the baseline is actually changes in albedo, which is primarily changes in the cloud cover, because the clouds are have the greatest contribution to the albedo of Earth. This, like I mentioned, the surface albedo of the Earth is about 13%, but the total albedo of the Earth is 29%. So the difference between 30 and 29, for the most part, is due to the fact that the Earth is covered something like 67% by clouds, and they are white and they reflect sunlight, right? So here is a paper that we just published a few months ago in August of this year. And the paper is entitled Roles of Earth's Albedo Variations and Top of the Atmosphere Energy Imbalance in Recent Warming, New Insights from Satellite and Surface Observations. This paper is quite long. It's 30 pages long. It derives this equation that you see here on the top that relates the deviations of global temperature to fluctuations in TSI and albedo. And the derivation is very objective, is actually kind of based on our fundamental equation that relates the temperature to pressure and TSI across the solar system, the red line that I showed before. It uses actually that, and through objective rules of calculus, it derives this equation. I will not go here in details. You can actually read the paper and find all the details there. But basically, we wanted to have an objective model that is independently derived and has universal nature, because this model should apply to any planet with a rocky surface in the solar system. It's not just specific to Earth, right? So we wanted to have a model like that to calculate what would be the implication on global temperature of the observed changes in albedo that has been measured by CIRRUS. CIRRUS is the satellite platform that has been in operation since 2000. It's the state-of-the-art platform that NASA has. So we downloaded the CIRRUS data. We downloaded the surface temperature data from 7 actually data sets, and we averaged them out, and we came with a representative time series of global temperature changes, global surface temperature changes since 2000. And then we applied the model to the observed changes in albedo and TSI as measured by CIRRUS, and we produced, a temperature record that we can compare to the actual observed temperature record on the surface. And here is the slide that shows this comparison. On the left-hand side, on the top, you have the decrease of albedo as measured by the CIRRUS satellites, right? The CIRRUS sensors. The graph on the lower right is the variations in TSI. And as you can see, the trend in TSI is almost zero. There are some changes, but it fluctuates up and down along with the 11-year cycle of the solar activity. The main thing is the albedo has a directional change. The albedo has been decreasing with a rate of about 0.24% per decade. So you can see here the total drop in albedo for this period of 24 years is about, if I remember correctly, is about 0.7% or something like that. So applying this model to those data that measured by CIRRUS, albedo changes and TSI produces actually a global surface temperature record that we can compare to the actual observed temperature record. And this is the graph that is shown here on the upper right. And as you can see, the model explains 100% of the warming. The observed warming for this period of 24 years is 0.23 degrees Celsius per decade. The model predicts 0.24 degrees Celsius per decade. So almost identical, right? The graph on the bottom, it shows just a scatter plot, the relationship between each of the values of the model and the observations in terms of temperature. And basically, it shows that the model explains 83% of interannual variations and 100% of the total warming. So that leaves no room for any greenhouse gas radiative forcing. Why? Well, because the graph here that shows the albedo, it corresponds actually to absorbed solar radiation, right? So as the albedo drops, the amount of absorbed solar radiation by the Earth increases, right? And the trend in the increase in the absorbed solar radiation actually is about 0.8 watts per square meter per decade, which is much, much larger than any calculated greenhouse gas radiative forcing. Well, the other thing is that if you take this observed increase in absorbed solar radiation, which is a real forcing, this is something measurable from the sun. You could not deny it. It's not a theoretical calculation, right? It's measured. If you take this rate of increase, 0.8 watts per square meter per decade, and you multiply it by the lowest sensitivity that IPCC has, climate sensitivity, which is in the order of 0.47 Kelvin per watts per square meter per watts per square meter. If you multiply, then you get a warming which is much larger than the warming observed. So that means, that there are those theories or suppositions or conjectures that, well, yes, the albedo has decreased, but this is a feedback, to the warming that already was started by CO2. So the CO2 is the underlying driver of the warming. And then, for some reason, one reason or the other, the albedo has dropped. So that comes on top of that. Well, if that's the case, the solar radiation by itself, the change in absorbed solar radiation by itself, or the change in albedo by itself, should produce a warming trend that is much less than the warming trend observed. So you have room for another forcing, which might be the CO2. Well, in this case, there is nothing left. The change in the absorbed solar radiation or change in the albedo 100% explains the entire warming, and nothing is left for any hypothetical radiative forcing from CO2 or anything else. You see? So this is explained in our recent paper in details. The paper also goes into a very interesting discussion about the Earth's energy imbalance, which is measured. It's real. However, we show numerically and through physics that this energy imbalance has been misinterpreted, meaning that it does not mean that the Earth is storing energy because of trapping effect of greenhouse gases. It means that the energy imbalance arises from the fact that the changes of surface temperature due to the change in absorbed solar radiation causes an energy flux that before it is being observed as a long wave flux on the top of the atmosphere, it has been attenuated to the troposphere because of the adiabatic cooling of the flux going up. So the energy imbalance is actually an artifact of this adiabatic cooling of the flux coming from the surface and going up, right? And we explained this in the paper. I don't have a graph about this. I didn't want to complicate too much the discussion, but it's an apparent energy imbalance, which is not the driver of climate. It's a byproduct of the processes in the atmosphere and the fact that you had increased amount of absorbed solar radiation by the planet because of a decreasing albedo. So this slide shows the full equation for the global surface temperature, which includes three parts. So you have, as before, I showed the first two parts before. You have the number one, you have the global temperature of a body without atmosphere. This is a hypothetical global temperature without atmosphere. You have the thermal effect of the atmosphere caused by pressure, which is term number two. And then the whole thing is multiplied by this other term, which accounts for the effect of changes in albedo and TSI on global temperature. It causes those little fluctuations of the global temperature around the baseline, And the baseline is determined again by average TSI and the total pressure, okay? So this is a complete equation that describes, and it applies to any planet, any moon, it's not just on Earth, that describes the global surface temperature on planetary bodies with rocky surfaces, and it has nothing to do, it has not even a term about radiative properties of greenhouse gases, atmospheric composition, anything like that. So on human timescale, basically, on human timescale, which means decades to centuries, the Earth's climate is driven by variations in the cloud albedo alpha, is this term over here. That's what we cause, that's the cause for the climate change that we have observed. That's the whole fuss about that, oh, the climate, we had a 1.5 degree warming from pre-industrial time or something like that, and the warming will continue to 6 degrees and we're going to fry and all that. No, we will not, because this term is controlled by cosmic forces, and there are feedback processes that limit how much this term can change. The albedo could not drop from 29% to 13%, because that means all the clouds should disappear. You could not have that. This could not happen. So when albedo drops and you have warming on the surface, you promote evaporation. That evaporation brings more water vapor into the atmosphere, and it acts as a negative feedback. So the albedo variations are limited, which is why we could not the planet could not be fried because of change in albedo, and likewise, it could not be frozen because of increase in albedo. In order to make the planet as warm, and we talk about this in a minute here, as warm as, for example, it was 50 million years ago when the global temperature was higher by 15, 16 degrees than today, you need a change in the baseline temperature, and that implies you need a change in the total atmospheric pressure. You could not achieve this warming by fluctuating albedo. Not possible, So the lesson here is that the climate change that we have observed has happened before. It's basically a fluctuation of the global temperature around a baseline value, which is set by the pressure and the solar irradiance. The pressure, according to our analysis, does change, but on geological timescales, not on periods of decades, centuries, not anything that is, that we're familiar on in terms of human perception. It changes on timescales of many thousands, tens of thousands to millions of years. So, okay. So then we decided to apply the extended model with respect to baseline temperature that not only predicts describes the global average temperature, but also temperatures in several key latitudes, with those additional equations that I showed through temperature gradients that are functions of the molar density, of the surface. We decided to apply this extended version of the model to study the paleoclimate, specifically the drivers of Earth's paleoclimate. So we followed the method of Richard Feynman, which he specified in a famous lecture, I think it was 1964, which was at Cornell University, or not sure which university was it, but there is a video about that where he describes this in a few words. He's a brilliant man. So basically, the first step is we come with a guess about something. We formulate a hypothesis. So our hypothesis was that changes in global surface air temperature observed in the geological record on timescales of thousands to millions of years are caused by variations in total atmospheric pressure and do not depend on greenhouse gas concentrations. Now, how we came up with this hypothesis? We came this with the hypothesis based on the understanding, our new understanding that arose from the analysis of the NASA data, that the baseline temperature of any planetary body is determined or fully determined by total pressure and distance from the sun, or a total solar radiance above the atmosphere, right? So on geological timescale, according to the best models we have of orbital variations and so forth, we concluded that there is no significant change in the difference. Actually, there is almost no change in the average distance between Earth and the Sun. That means the geological climate is the changes in geological climate are not driven by changes in the solar luminosity. And the only other parameter left in our equation, in our model, is actually pressure. So that's how we came up with this hypothesis that it's probably the changes in total pressure, total atmospheric mass, that are responsible for the huge changes in climate that we observed in the geological record. Okay, so that's our hypothesis. According to Richard Feynman, we have to come up with a method to calculate the consequences of this hypothesis and then compare to observations to see if it's true, right? So the consequence about this hypothesis is that a model assuming variations in total atmospheric pressure as the main driver of Earth's paleoclimate should correctly reproduce a phenomenon that is known as polar temperature amplification in the geological record. Polar temperature amplification refers to the fact that in the entire geological record, doesn't matter if you look at the period of the ice ages, the last million years, or you look longer, the last 60 million years, the Cenozoic, you have a phenomenon where changes in the temperature, in the global temperature, not global temperature, but changes in the temperature of the equator are always much smaller than corresponding changes of the poles. That's why this is called polar amplification. This is ubiquitous observation. In the entire geological record, you always have this when it gets warmer, on time scales of millions of years, for example, or tens of thousands of years. When it gets warmer, the variations of the equatorial temperature is much, much smaller than the observed variations in the polar temperature, okay? So this is our test, how we're gonna test the hypothesis that maybe pressure is the driver of the Earth's climate on geological timescale. So then we have to compare the model computations to observations. So this is the verification of our hypothesis. And the verification is that if the model correctly predicts independent reconstructions of equatorial and polar paleotemperature dynamics, which means the past polar amplifications as observed in the record, then the above hypothesis is verified. So, okay, so here is the record. There is a more updated version of that record, but it'll suit now for this presentation. This is a global temperature changes based on several sources that I obtained the data from, and the temperature here is presented as absolute global temperature, not anomalies, but absolute global temperature in terms of Kelvin on the left-hand side or degrees Celsius on the right. And this shows a period of about 83 million years. Now you can see that speaking about humongous climate change, this is the climate change that actually deserves attention. We are right now, in the one of the interglacial periods, the Holocene. It's right here. You could not even see it, but I showed here from 1850 to 2017. That's this band here of orange, of reddish hue. It shows the global temperature change in those periods from 1850 to 2017. Compare this to the huge changes in temperature in the geological record. So basically, since about 50 million years ago, the Earth has been cooling. And 50 million years ago, the global temperature of the Earth was about over 31 degrees Celsius, right? There is a period 56 million years ago called the Paleocene Eocene thermal maximum, and at that point the temperature went even higher. It was like 33 degrees. More recent data show even 38 degrees Celsius. So we're talking about a planet that, in terms of climate, was a basically totally different planet, nothing to do with today. So we've been having this, and before that, during the dinosaurs was even warmer. I don't have here the graph, but I have a more up-to-date graph that goes to 105 million years. And yes, during the between 90 and 100 million years, the temperature was even higher than during the early Eocene. And, you know, this was a time when the dinosaurs were proliferating on Earth. And, you know, it basically had a subtropical vegetation in high latitudes, you know, around the northern part of North America and Alaska and, you know, the Antarctica. And also there was no ice on Earth. Now, ice started appearing on Earth about like 40 million years ago. That's when the first, and then the first glaciation of Antarctica happened about 34 million years ago. So before that, before 40 million years ago, there was no ice and no snow on Earth for millions, tens of hundreds of millions of years, at least tens of millions of years, all right? So we're talking about humongous climate change, right? So we will focus our attention to two periods. One is the early Eocene, which is about 51 million years ago, marked here with the circle. And the other one would be the ice ages, you know, the fluctuations of global temperature during the ice ages, or the ice age cycles, okay? So what is the polar amplification? So here, this slide shows the polar amplification actually during the ice ages on the left and during the early Eocene on the right. So if you look the graph on the left, actually is a time graph. On the vertical axis, you have the anomaly, temperature anomaly from the present, and you have two curves. You have the red curve is the temperature anomaly observed on the equator or in the tropics, and the blue curve is the temperature anomaly observed at the poles. Now, this is average between the two poles, north and south, Arctic and the Arctic, okay? It's not just one pole, all right? I won't go into how this is calculated, but, you know, there is an objective way that we did it, and we calculated that. So just take my word that this is actually the fluctuations of the average polar temperature on Earth for the last 780,000 years, okay? So what is a polar amplification? Well, if you look the variations, because those are amplitudes from the present, plus minus around zero, if you look at the variations of the polar temperature, the red line, they are much, much smaller than the order of, you know, between what, 2 to 4 degrees compared to the polar regions where the fluctuations reach, you know, close to 12 degrees, right? So this difference in the fluctuations of global temperature between the poles and the equator is actually the polar amplifications during the ice ages. And I marked this with a light blue. This is the air. This is the difference, right? The light blue. Okay, the graph on the right, it doesn't show things in time. It shows just in one, or it's kind of an average period in the early Eocene. Those data from publication by Tierney et al. 2017, Eocene temperature gradients in Nature. So on this graph, you see the reconstructed temperatures using different proxies. For the early Eocene is the blue line. The individual points are individual reconstructions, but the blue line kind of shows the average change of temperature with latitude. And this is average between northern and southern hemisphere, right? So we have absolute latitude. 0 is the equator, 90 degrees is the pole. And you can see that there is a slight decrease of temperature between the equator and the pole, but it's nothing compared to the current temperature of the Earth, which is the pink line, right? This is the current temperature representing the average of the temperatures between 81 and 2010. Again, average between the two poles. And you can see here that at the equator, you know, back 50 million years ago, 51 million years ago, the temperature at the equator was about 9 degrees warmer than today. Yet at the poles, the temperature 51 million years ago was over 37 degrees warmer than today. This is the polar amplification that I'm talking about. So the temperature has, as the planet cooled over the last 50 million years, the poles cooled much, much more than the equator, right? So now, on the left here, you see a reconstruction of the global temperature during the ice ages. And this comes from two references, Snyder and Frederick. They're both 2016, two independent reconstructions, but they're very close to each other. So I averaged them out. And this is the average between the two time series. And it is the absolute global temperature during the past 740 million years. And you can see the cycles of ice ages, right? The 125 million years, 125,000 years ago, this period, previous interglacial is called Eocene, and it actually was warmer than the current Holocene. The Holocene is right here, where the last point right here, right? But there were other periods that were also warmer, like 400,000 years ago. That's the Holocene, I believe it's called, and most of them actually they were cooler than today. But the ice ages are the lowest points in temperature here, and you can see there has been a variation of about 7 degrees or so in the global temperature, 6 to 7 degrees in the global temperature between interglacial and glacial periods. Now, the assumption that we make here is that those changes in global temperature, they actually caused, this is an assumption, this is part of the hypothesis, right? They're caused by changes in pressure. Well, the question then is, what are the changes, what is actually the changes in pressure required to achieve this change in global temperature? Well, the graph on the right uses our model, our original model actually, that relates the atmospheric temperature, that relates the surface temperature to pressure and total solar radiance, right? The baseline temperature. It inverts that equation and solves it for pressure using the temperature record on the left. So we're using the temperature record observed one as input, and we're calculating what will be the required change in pressure according to the model derived from the planetary data that I showed before. What will be the required change in pressure to achieve this change in temperature? Okay, so the graph on the left shows the changes in pressure. Changes in pressure are quite substantial. We're talking about 30% or so drop of pressure between interglacials and glacial periods, right? So then we applied the extended model that has the calculations based on the changes in pressure and temperature. That gives us the changes in surface density, molar density of the air, which actually allows us to calculate what will be the changes in the meridional temperature gradients on the planet as the pressure changes, right? So here is the result from those calculations, where our extended model allows us to calculate the changes in the equatorial temperature and the change in the polar temperature, right? And we're comparing those changes in the equatorial and polar temperatures to actual observations from the geological record derived from proxies, okay? So the model, the equatorial temperature here, the model is the dark red, and the measured equatorial temperature changes is the dark red, and the model is actually the light red, right? And you can see how close the model follows the equatorial temperatures. The same thing on the polar temperatures. I put them on one graph so people can actually see the difference between the poles and the equator. And here, on the polar temperatures, the measurements are in dark blue, and the model calculations are in pink, right? And you can see that the model is capable of predicting the magnitude actually of changes in polar temperature. And those magnitudes are much larger than the magnitude of change in the equatorial temperatures. So the model is basically able to reproduce the polar amplification that is observed in the geological record over the last 740,000 years. This is the goal that we wanted to see, how well an assumption that pressure is the driver of on this time scale of the global climate, how well this assumption can actually predict the polar amplification, and it predicts it very well. The graph on the right, it shows just a correlation between observed polar temperature anomaly and modeled polar temperature anomaly. And you can see the correlation is 0.84, which is pretty high, right? Now, going to the early Eocene, 51 million years ago, this is the graph that I showed before. So here you have the blue line, the blue dashed line is the average variation of temperature with latitude that is derived from the proxy record, from the geological record, right? The line in dark gray, the one that goes below the observations quite a bit as you approach the poles. Again, you know, on the x-axis we have the latitude from equator 0 degree to the poles 90 degrees, and on the y-axis we have the mean annual temperature for that latitude, right? So here we can clearly see, and this is very well documented in the scientific literature, that climate models, this gray line is the average of a number of Eocene model intercomparison project models. I don't know how many models are in there, but there are several models that are specifically designed to simulate the paleoclimate. So they average the output, and this is a well-known phenomenon that models fail to reproduce the warmer polar regions that are actually observed in the geological record. If the model comes close to reproducing the equatorial temperature, and again, the models are driven, climate models are driven by CO2, right? They're entirely driven by CO2. If they come close to reproducing the equatorial temperature, they fail completely to reproduce the polar temperatures where the model predictions are way lower than actually temperatures inferred from the geological record. The red line here is our model, okay? Is our model that assumes a much higher pressure existing at those times. Now, the standard climate models, they only play with the CO2 and its so-called radiative forcing, and they use the same pressure as today. The climate models do not assume any change in pressure from today's environment, right? So our model, however, we estimated that in order to reproduce correctly the global average temperature, one value, global average temperature 51 million years ago, we should have a pressure of 275 kilopascals, which is about 2.75 higher than today, 2.7 times higher than today. Using that pressure and using the extended version of the model that predicts the temperatures of different latitudes, we're able to produce this red curve, which, as you can see, matches very closely the observations from the geological record. So in other words, the assumption of a higher pressure during the early Eocene enables us to produce, to correctly calculate the difference in temperatures between the equator and the poles that were measured in the record for that period, for that era, 51 million years ago, okay? Now, this is kind of conclusion. So this table shows the principal differences between standard greenhouse hypothesis and our new climate concept. Number one, the overall thermal effect of Earth's atmosphere is about 33 degrees. That's what the greenhouse hypothesis claims. We have found, analyzing data of the moon and doing deriving correct formula for the reference temperature of no atmosphere temperature for a planetary body, we have found that the overall thermal effect of Earth's atmosphere is about close to 90 degrees, right? Second, the atmosphere, according to the greenhouse theory, the atmosphere warms the surface of the Earth by impeding the loss of radiant heat to space through absorption and re-emission of outgoing long-wave terrestrial radiation by trace greenhouse gases. This is what the greenhouse theory claims, right? What we have found is that the atmosphere warms the Earth's surface adiabatically through the force of air pressure, which it enhances the energy received from the sun in a way analogous to the compression heating. Earth's surface is under a constant gas compression, and everybody should realize that. Third, according to the greenhouse gas theory, the Earth's global temperature is sensitive to changes in atmospheric concentration of trace greenhouse gases. Thus, human-induced carbon emissions can affect climate. Well, our new paradigm actually shows that Earth's global temperature is absolutely independent of atmospheric composition. Non-condensing trace gases do not have a measurable impact on climate simply because their partial pressures are very low. Thus, the sensitivity to the climate system to human-induced carbon emissions is essentially zero. And that point is not being accepted even by the skeptics, and I'll talk about this in a minute. Finally, according to the greenhouse theory, CO2 is a control knob of Earth's climate on virtually all time scales. In fact, there was a paper published in 2010 by Gavin Schmidt and company that actually uses that. They introduced that term that CO2 is a control knob of climate, and you're familiar with that, and a lot of people know that. So it doesn't matter if you're talking about changes of the climate or changes in global temperature over the last 60 years or the last 60 million years, it's all CO2. Well, the geological record does not support at all the notion that CO2 has any role to play in the geological climate change, but that's a different topic. I won't talk about this today. According to our paradigm, Earth's climate is controlled by different forces on different time scales. So sun-induced changes of global cloud albedo through Birkeland electric currents and magnetic modulation of the galactic cosmic rays flux are responsible for the observed decadal to centennial fluctuations of climate. Changes of total atmospheric mass and surface air pressure drive climate dynamics on timescales of thousands to millions of years. So this is the principal differences between the greenhouse theory and our concept are like day and night. They don't have anything in common. And again, our concept is not based on conjectures, it's not based on thinking about a phenomenon, it's not based on a thought experiment, because the greenhouse theory originally came as a thought experiment, was proposed by Fourier in 1827. Later, they did some measurements and they saw that CO2 and water vapor absorbed some infrared radiation. They said, oh, there you go. So those gases act as a blanket to stop the cooling of the surface to space, and that idea persists to this day. It's absolutely ridiculous idea. You could not trap heat in an open system. It violates the second law of thermodynamics. Try to remove the roof on your house in the wintertime and see how much heat you can trap by emitting CO2, right? So, okay. Bumper sticker. New science. What causes climate change? It's the cloud albedo and air pressure, stupid, not CO2.
I'm just curious, based on what you know, do you have any predictions for what is going to happen in the next couple decades or the rest of the century in terms of warming or cooling?
So, like I pointed out, the key to understanding what will happen in the future with climate change, and we're talking about human timescale, decades to centuries, we have to understand what's driving the cloud cover. And that knowledge, we have ideas, we have hypotheses, but it's not at the point where you can formulate it in math equations and put it in a model and be able to predict that, because this relates to the the likelihood is like 80% and above that changes in the cloud cover are caused by cosmic forces through the sun, one way or the other, okay? The galactic cosmic rays are probably also involved, but we have empirical evidence that this is the case, but we don't have a specific exact mechanism that we can formulate in mathematical equations and put them in the model to have a predictive model. So based on past observations, I can say that nothing goes up or down like warming or cooling indefinitely. We are because we've been in a warming phase for 150. You can actually claim close to 300 years. Most likely there will be a reversal, and when this reversal happens, it can happen literally within a few years. It will not take like decades to start. I mean, I'm not saying that the temperature within a few years will go down to the level that was in the 1700s. I'm not saying that. I'm saying that the trend can reverse real quickly when the cloud cover changes, right? So and this is the thing that we recommended very boldly in our last paper from 2024 that was published in August about the effect of albedo and Earth's energy imbalance on climate. We recommended that the efforts and the funding should be focused on understanding the drivers of the cloud cover and the drivers of the cloud albedo, not on CO2, not on carbon emissions. This is a waste of efforts and money. Now, I want to point here something very interesting. I think that this is not related specifically to your question, but we presented this presentation we gave about a month ago to Clintel. Clintel had this is a skeptics organization, probably all the people that are listening to this show, they're probably aware of that as well. They are international nonprofit organization, I think. And they had a conference in Prague, and we participated remotely. We didn't travel to Prague, but there were conference was physical conference, and they had it actually in the parliament building, believe it or not. They were able to secure that venue. So we made a presentation there, and it was a little bit shorter version of what I present, but the essence was the same. And it was received with hostility, I would say. It's not everybody, but majority of the people expressed opinion, because we had also exchange over the email, even before the actual presentation. Then after that, we had tons of email exchanges. Most people are still clinging to the idea that CO2 has some role. It has to have. Well, we've known this, for 200 years. Well, it has to be something, maybe not big, but a little bit, right? And so this was the majority of the opinions. I could not hear one person, maybe they had this opinion that CO2 has no effect, but they didn't have the guts to say, we think that. Okay. However, what is worse, that some of the leaders, so to speak, or the organizers of the conference, specifically Lord Monckton, who is a famous skeptic, he called us in front of everybody disruptors for having the courage to present this concept that actually shows that CO2 has no effect on climate. He called us disruptors. And so my impression is that it's not an impression, it's actually experience. And people should understand that in the whole, all the skeptics pretty much across the board. I don't know if there are some exceptions, maybe they exist, but I don't know them. Everybody that Roy Spencer, Richard Lindzen, Happer, Monckton, Judy Curry, John Christie, you mentioned, everybody, they only say that, well, the CO2 is not a problem because the warming that it causes is small, right? But they never give up the fundamental ideas and premises of the greenhouse theory. They believe in the radiative greenhouse effect, which is a physical nonsense, like I showed here. It contradicts fundamental physics. It contradicts, what's happening in the atmosphere, and they cling to that idea. And some of them, like Monckton, are openly hostile to people that would like us that express something different. I mean, why? There was a funny situation at the end. They wrote a communique, like a summary, conclusions from the conference, and there was a sentence there that says the CO2 is causing climate change. I said, there is no evidence for that. This sentence is not needed, because if you want to present something new, you have to go away from that message, because that's false. He said, this is your opinion, nobody else agrees with you. Let's take a vote. How many people think here that CO2 has no effect on climate? Let's see. Okay, no hands. You alone. So Monckton thinks that you can decide science by voting on it. I'm not kidding. This was in front of, you know, a big audience. So people need to understand that the skeptics community is not actually what it appears to be, in a sense that they're not looking for a solution. They are interested. My impression is that there are groups, not maybe all of them, but there are groups that are interested in kind of promoting the status quo, just saying, oh, IPCC, this and that, we don't agree, blah, blah, blah. But they're not attacking the fundamental, which is the greenhouse theory, which is the cornerstone of everything, all the economic changes that are being proposed, net zero and all this insane stuff. It is built on that. If you remove that cornerstone, everything collapses. And we have the science now. We have with actual data to show that. And there are climate skeptics now. Moncton is not a scientist. You know, for example, I would say about Happer that he knows very well our research, because I sent him all the papers. I discussed some stuff on, but he's never been public about that, saying out those people don't know what they're talking about, or criticizing us public. He's never said that. He's a very polite man. I respect him for that. But he knows our research, but he never said anything publicly. Moncton is not a scientist. He openly told us disruptors, and he openly is trying to basically to denigrate, you know, all our research, you know, and say that this is not true, you know. Oh, look at Happer's paper. Well, okay, I address the Happer's papers here, you know. This is what they believe, but it's not what actually is happening in the atmosphere. So anyway, you have another question.
Just maybe the last question is, over the course of 20,000 years since the last, the depths of the real ice age, do you think pressure is the major reason for the warming since then, since it's more of a long-term change?
Right. According to our calculations and the fact that this hypothesis that we had of changing of pressure correctly to produce the observed polar amplification, we believe that there has been an increase in total pressure from 20,000 years to the present. Now, during the Eocene, the pressure change basically stopped, right? Because we are now in a kind of, if you look at the temperature during the Eocene reconstructions, we're kind of going down, but it's very, very slightly, you know. It takes thousands and thousands of years before actually you see the drop, right, in temperature. It doesn't happen in decades. So I don't think this is something we have to be concerned about, but yes. And the other thing which I didn't mention is that if you assume for a minute, which there is no data to support that, but if you assume that it was the change in the solar luminosity that has been causing the changes in the, global temperature during the ice ages, and you apply that idea, pressure being, you keep it constant, but you change the solar luminosity to the point that it can reproduce the changes in the global temperature, what you get is that the larger changes in the temperature occur in the tropics and smaller changes in the equator. So you get the exact opposite of what is observed in the geological record. You get the exact opposite of the polar amplification, if the solar radiation was the driver, which is another data point that actually strongly suggests the solar radiation was not a driver. And we know from, the results from the Milankovitch cycles, there is a group in France, Lashgar and company, that their whole research over several decades has been actually to refine the orbital models, right? And I have the output from their models, and it clearly shows that the average distance between the Earth and the Sun basically changed so minuscule that you can ignore it for this period of last million years. There is some variations, but there's so minuscule, and there is no correlation between any of the orbital parameters, eccentricity, tilt, precession, and the global temperature. I have actually made a post a few years ago, now 2 years ago, I think. It's in the Tollblock discussion post, Roger Tollblock, where I showed numerically, the best available evidence that we have for the change in global temperature during the ice ages, and correlated this with the known changes in the orbital parameters. No correlation. Like correlation is like 0.2 or less, nothing. And yet this myth persists that, well, the ice ages are caused by orbital changes. No, it's not. The data do not support that at all. So
I just pulled up an article that says maybe 300 million years ago, there was a dragonfly that had a wingspan of 28 inches. Is
Yeah.
that an indicator that there was more pressure then and it was easier to fly? And then another part of that is, how do we know what the pressure was 20,000 years ago or 300 million years ago? I might have missed that, but how do we know what the atmospheric pressure might have been long ago?
So the analysis that I showed for the ice ages and the early Eocene, I basically take the temperature that is observed in the geological record, like the temperatures, and I run them through our equation by inverting the equation and solving it for pressure. Okay, so the equation that was derived through the planets, I use that equation to calculate what is the required pressure to achieve that temperature that was measured. Okay, so that's how the pressure calculation that we have, it's not measured, it's reconstructed. Yeah, but then the implication of this reconstruction is the polar amplification, which we predict and then we compare against independent measurements, of the polar and equatorial temperatures. Those are independent measurements. Some people don't understand this fine detail. Say, oh, you're calculating the pressure from temperature, and then you're comparing temperature against. No. We're calculating the pressure from the global temperature, and then using the global temperature and reconstructed pressure to compute what is the change of the temperatures in the equator and the poles. And equatorial and polar temperatures, we're comparing to independent data. And that's how we assess so.
Okay.
So about 300 million years ago, I think I think it was 360 million years ago when we had a cold period very similar to today, to today's ice ages, right? And I think the 300 million years ago, I think it was warmer than the present. But the other thing is that why you have those huge insects was not just the warmth. There was much higher oxygen concentration.
Oh, okay.
It is the oxygen concentration that makes actually things grow bigger.
Very good.
It's not only the oxygen concentration, but actually is the partial pressure of oxygen. And partial pressure of oxygen is the concentration times the total pressure. Okay, so if, for example, there is a very interesting analysis done in the late 90s. There were two researchers from the U.S. Geological Survey. What they did, they retrieved samples of amber from different time periods in the past. And those amber, they have bubbles in them, air bubbles, right? So they crushed those air bubbles in a vacuum chamber, and they wanted to measure the concentration of gases. They could not measure the pressure, but they measured the concentration of gases, and they reconstructed, the concentration of oxygen going back to about 140 million years ago, right? And this period during the proliferation of dinosaurs, 100 million year to about 83 million years ago, the concentration of oxygen was like 35%. It's 21% now. Now, the physiology of animals responds to partial pressure of oxygen, not the concentration itself, right? So with our analysis that calculating what was the pressure at that time, and the pressure was close to 3 atmospheres, right? If you multiply that pressure to the concentration, the higher concentration of oxygen, you get a partial pressure that is almost equal to the total pressure of the atmosphere today. About 4 times higher partial pressure compared to the partial pressure today. So that explains why you can have animals of this size, because those animals so basically I think the ecosystem back then was running on steroids because of the high oxygen partial pressure.
I do need to let you go, but thank you for all you've done here. I'm excited to put this up and get some comments on it, but I appreciate it. Ned Nikolov.
Thank you.
Talk to you next time. Goodbye.